Okay, so good morning everybody. Today is the third lecture on Markovian open quantum systems, and I would like to start with a summary of the previous lecture. Then we shall at last reach the top of the mountain. That means the general equations governing Markovian open quantum systems, essentially the most general equations you can write down. And then I'll go for a few applications, and one of the applications will be to a real experiment. So, first of all, are there questions about the previous lectures? No questions. Perfect. So, to make a summary, so the main result you obtained last time, we did essentially two things. We studied indirect measurements, and we had an application to progressive collapse. Our starting point today will be indirect measurements, so I will come back to it in a moment. I would just like to say a few words about applications to progressive collapse. So what we were able to show is that we already had the tools to model a real experiment, and in this real experiment the use of probes allowed to construct somehow little by little a macroscopic measurement apparatus. Each probe by passing by was enlarging the size of the Hilbert space with which the cavity was interacting, and as the size of this Hilbert space gets large, one gets a macroscopic measurement apparatus, and one observes a wave function collapse. So there are two comments that I need to make about that. The first one is that the computation I presented, in fact, are the result of a collaboration with Denis Bernard. So these are not my computations, but these are neither other people's computations. It's a bit a problem for me to present personal computations in lectures like that, but it's a good illustration, I think. And the second thing is that at no point do I claim that we have proven or explained wave function collapse. Because remember, the measurements we do on the probes are just the standard measurements of quantum mechanics, non-linear whatsoever. So there is really no claim that we have a conceptual framework in which we can forget about this dilemma that we have unitary evolution sometimes and projections and measurements at other times. This is a dilemma that still remains after our computation. What is very, very nice is that the use of indirect measurements allows to build the measurement apparatus somehow little by little, and somehow to have time plays the role of size in a certain sense in this discussion. And as time goes by, in fact, the system is in contact with a larger and larger measurement apparatus, and the wave function collapses at some point. Okay, I think this is enough for what I wanted to say about the previous lecture. So we go back to indirect measurements, and let me just recall our main result. So we go back to A, and I will try to write larger equations. So we had A, which was the system of interest. B was a single probe. We had some unitary evolution which was on the Hilbert space of A tensor the Hilbert space of B. We had the measurement operator lambda, which was equal to 1 on HI tensor something I should call lambda B, and I had a spectral resolution which was something like lambda b is equal to sum over I think this is with the majuscule capital letter, and it was lambda I. This is the basis of B. What else did we have? We had a density matrix, rho, which was equal to, okay, rho A times rho B. And we decided to diagonalize rho B by writing rho B is equal to sum over I of Pi I, and this is also a basis of. Okay, so these were our ingredients. And so the idea was that we wanted to measure this. This was used to evolve. This was used to measure. And the outcome is that if we define V ij to be equal to square root of pj I u j. So this is still an operator which operates on A. Let's say HA. And the result was that eigenvalue I, or lambda I if you prefer, is obtained with probability sum over J trace over Hilbert space HI of V I J rho A V I J dagger, and afterwards rho prime A, or let's say rho prime is equal to rho prime A tensor II, and rho prime A is equal to, we can guess, sum over J V ij rho A V ij dag divided by the trace HA sum over J V ij rho A V ij dag. Okay, so this is the summary of indirect measurements. And now what we would like to do is to understand what is the general structure we have there and how general the equations we have are. Yes?
Why do you use the factorized state y product rho B?
Oh, this is just this idea that, well, this is an assumption, of course, and this is just this idea of, we have in mind a a situation in which at some time A and B are far from each other, so they are independent, rho eta and rho b, then they interact with each other, and U is creating correlations or whatever between, or coherence or whatever between A and B, and this is why when we measure we get a non-trivial result. So what we say is that in fact it is a period of interaction between the two systems that creates all the correlation, entanglement, and whatever. Okay. So this is an assumption.
This is just the initial state. Yeah.
Yes, this is just the initial state. If we would not include the evolution, if you put the identity operator here, you will easily see that essentially nothing happens to rho A. So this is just saying that. So you can imagine that this is a diffusion. You could think in particle physics as a diffusion of two particles, one on the other. But in particle physics, essentially, you try to measure the state of both particles after the interaction. In this philosophy, you measure only B, and you try to learn something on A by measuring on B. But apart from that, the picture you should have in mind is some kind of collision, and in the relativistic sense, you would send the two particles on each other, but in the relativistic context somehow. But in our context, essentially, we view A as fixed, and then we send the probe B on it. But it's exactly the same. I mean, it's more efficient in high energy physics to not to have particles at rest, but two particles colliding each other. But it's a question, just a question of reference frame, of course. Okay. So let us go to an important special case. So somehow it looks as if there are as many i's, capital I's, as small j's. But in fact, this is not really the case, because here you have this square root of pj. I'm sorry, yes, this is the density matrix. So in fact, you could also take a pure state. So the special case is when rho b is pure, equals to something like psi, and then what we get is that it's easy to see. Then if I translate the above equations, so let me put this in red here, and then if I translate on the same blackboard to spare some room, essentially we have, okay, so I should then define simply this would I would just define Vi to be by definition I U psi, and then the equations would be this equation would be replaced by trace over Hi Vi rho A Vi dag, and well, all the indices J would disappear essentially. This would become rho prime A equals Vi rho A Vi dagger divided by trace Vi rho A Vi dagger. Okay. So, which means that somehow there is so in fact there is no we do not have to think of the index sets I and J as related to each other. And one of the important properties, anyway, whatever happens, is that if I do the sum over I, J, V, I, J, rho, A. I'm sorry. V, I, J, dag, V, I, J. I always get the identity on the Hilbert space Hi. This is a constraint that we observe all the time. And this is needed, this is in fact equivalent to conservation of the trace. Okay, so now this raises the question S is a finite index set and operators VA are given for A belonging to S such that sum over A VA dag VA is equal to the identity on some Hilbert space H. And we assume that S is finite and we assume that dimension of H is finite as well. And then the question is there a way to construct a Hilbert space, a probe-Hilbert space somehow, for which the VAs that appear here are exactly given by such a construction? So we wonder whether we can, in fact, by this procedure, achieve any solution to this equation. Okay, do they appear as the result procedure? And the answer is yes. And to quote things precisely, take K a Hilbert space such that dim of K is equal to the cardinal of S. Okay. Take psi, a unit vector on K, and take an orthonormal basis of K. Let me finish here. Then there is a unitary U on H tensor K such that VA is equal to A U psi A belonging to S. Okay, so this says that in fact by this procedure we can study any situation can appear. I mean, mathematics do not put any constraints on this construction, The only constraint is, well, you might say, okay, you guarantee me that there is this unitary, but this unitary doesn't represent any interesting physical system, or it's arbitrary, whatever. That's very possible and even likely. Nevertheless, mathematically, if you give me such operators, they can always be realized as the effect of making an indirect measurement after a unitary evolution. So this is a little theorem which is easy, and the proof will be in the notes. I don't want to give the proof because it's pure mathematics. But it's easy. I mean, it's easy.
Sorry. To what extent is U unique or not?
Oh, very, very non-unique.
Is it fixed by parameter counting?
I don't know. What is clear is that it's extremely non-unique because, well, you see, you only fix the matrix elements between a vector and the basis. So it's extremely modest. So essentially, the proof consists in observing that this relation here is just part of the equations you would write down to say that a certain matrix is unitary, and then you complete. So essentially, it fixes. Okay, so basically, U has S squared coefficients somehow, and well, no, I don't want to say it. Okay, you can do a parameter counting. I prefer not to try to do it on the blackboard because I would say stupid things, but if you look at the proof, and it will be in the notes at some point, it tells you how to do the parameter counting. But there is a lot of arbitrariness in U, in fact. Yes, I hope I'm not saying something wrong. Now, you're perturbing me, Jean-Marc. Just a second. Okay, so let us go on. So now let us make a second remark. No, let's skip this. So now, if we do this, we are going to end up exactly with these equations, but with the index I is going to be played by little a. Now, let's think. So we have this formula or that one, and now let's think of looking at this formula and doing partial measurements. So I'm sorry, partial observation of the result. What does it mean? So now we have S, we have A belonging to S, and now we partition S is equal to union over R of SR, and it's a partition. And if A is measured, by this I mean that we have an observable lambda which is equal to sum over lambda A AA, and all these and so when I say A is measured, I mean lambda A is measured. Okay. So if A is measured, then so we have rho prime A is equal to VA or VA dag divided by trace VA rho VA dag with proba trace of VA rho VA dag if the result of the measurement is observed, yes. And on the other hand, what we will find is rho prime A is equal to sum over A belonging to SR, VA rho, VA dag, divided by trace VA rho. If observe trace over A belonging to SR, and this is proba sum A SR VA rho VA dag only lambda A belongs to SR is observed or recorded or whatever. I don't know. I have a problem between measurement, observation. I mean, this is vocabulary, but you see. So these are two possibilities, and the extreme, as I already said, of course, if you take for the partition, you take the singletons, you recover this, and if for the partition you take only S itself, you recover purely the average. Okay. So what I wanted to stress is that, in fact, if you look at this formula, you see that at the level of the level of rho A, it is impossible. It looks the same to make a partial observation of the result with rho B a pure state or to make a complete observation with rho B a density matrix. What do I mean by that? Well, look. Well, it's not. You see, if now I interpret, so if now I say that I'm going to look at this piece here, and now I say, okay, let's say that S is the set of A's, and it's exactly equal to the set of pairs ij, okay, of couples ij, okay? And now I say that R is equal to, what is it? I guess capital I. This is going to be fixed. Yes, okay, and I say that the set of R's is the set of capital I's. You see that this formula here, these two formulae are exactly those two formulae. But here what we do is do a partial reading, and the initial state for B was just a pure density, a pure state, psi. And here we have taken a density matrix for rho B, and the effect is exactly the same on A. But beware, this is important. Well, I think this is an important distinction, but beware, in the first case, the full density matrix isn't factorized between A and B, whereas in the second case, okay, so in the first case, somehow if we are in the second case, in fact, we let the interaction takes place with the Hilbert space whose size is the size of the number of i's, capital I's, and here we interact with an Hilbert space whose size is the square of that number, essentially. Okay, but then afterwards, even if on A the result is exactly the same, the complete result is that there are still there are still correlations between the probe and the system after the measurement when you do a partial reading, and there is no correlation between A and B when you do this operation there. Okay, so this is a remark I wanted to make, and then comes a last mathematical theorem, and which is a crucial question. Does it make sense to iterate the equations? Okay, we have now a family of equations which are quite general. There are these equations, and the question is whether or not it makes sense. So you see, we started from rho A and we went to rho prime A, and the question is, what is the physical meaning of iterating these equations? And the answer is maybe totally obvious, and the answer is it depends. Which is a good answer to essentially any question. And modeling successions of independent probes iteration is the real evolution. Okay. Now, if the successive probes are not independent, but almost independent then Markovian evolution iteration is a good approximation. This takes a small computation, you see. It's not the fact that we say, okay, if I start from rho A, then rho prime A is this, doesn't mean that if I do it again with the probe, I mean, you have to do the computation, and it's really crucial that the evolution for each interaction with the probe only acts on the space of A times that probe and nothing else. And you have to do the computation up to the end. You cannot as I told you, the time evolution and taking a partial trace do not behave very nicely with respect to each other. So this is really an exceptional situation that it works that way. You can really do the unitary evolutions and the partial traces independently of each other, just for the reason that the interaction is really only between the system and the probe, and not with the other probes. Okay, and now to model contact with the reservoir, it depends again. So imagine you are in the following situation, that you have a big reservoir this would be what I call, well, I don't know. This is what I would call the environment. And here I have my system A. Here I have some kind of piston, let's say. And I shouldn't write it that way. I have some kind of piston. And here I have a few particles. And here I have many particles. See? And now the question is, so what we know is that if we look at the evolution for one time step, this is going to the Markovian. Well, no, it's not, we don't have to talk about Markovian, but somehow, so we know that. So first of all, we have to discuss. Well, we have to discuss many assumptions. The first point is that if A is very small, with respect to the environment, we can neglect the back reaction of the of A to E. Okay, so this means essentially, well, and this means that as time goes by, one has always a factorized rho A tensor rho E, and this one is essentially time independent, and this one changes with time. So this is essentially because we assume that there is no, it's too small to have a back reaction. Okay. And then what happens then? If you look at a certain time interval, some of the molecules of the gas, you can even think classically in that game. If you look at a certain time interval, a certain number of molecules from the environment will come and hit the piston and do something, and then they will go away. And as they go away, I mean, when they hit the piston, they have some interaction with A, they get correlated with A, whatever. So, but then they leave, and they start to experience collisions with the other molecules. And so basically, now, the Markovian approximation is good if the degrees of freedom that interact with A, degrees of freedom in E in the environment, they interact with A between T and T plus epsilon and between T plus epsilon and T plus 2 epsilon, let's say, are essentially independent. And the point is that now you have two typical times. Capital T, which is the time freedom. So the time it takes to a degree of freedom in the environment to interact again degree of freedom of the environment to interact again A, and you have another typical time, let's say tau, which is some kind of collision time. The time it takes to a degree of freedom to lose memory somehow. And you see that Markovian is good if T is much, much larger than tau. So what it means is that, you see, a particle comes, hits the piston, and then goes away, and then has many, many, many collisions. It takes it an awful lot of time to diffuse in the system, and then much, much later it will come back again, but it will have forgotten everything of its past, and it will interact just as new with A. So you see, well, you can do a much better discussion. I mean, this is really à la hache, I would say in French. But basically, there can be good reasons to believe that even for the contact with an environment, the Markovian approximation is a good one. Okay, so probes, independent probes, Markovian approximation is perfect, and contact with the environment, Markovian approximations is depending on the relative value of certain time scales, it can be a very good approximation. Anyway, we shall take the formula that I will recall now as the starting point of our all our further computations. So let me write them down. I wrote them already during the first lecture, but let me write them down once again. So it says that, so you have rho A goes to rho prime A equals SR rho VA rho VA dagger divided by trace. Okay, so let's and in fact let's introduce time because we want this to be Markovian evolution divided by trace. Okay, so maybe it's okay. I think I can do a bit better. Now we can, so now from now on, we concentrate on A, and so we suppress A indices. So now it's rho, and so it's just rho at time n, step n, and it gives rho at step n plus 1, which is VA dagger, divided by trace, sum over A belonging to SR VA rho n VA dagger, with proba trace, sum over A belonging to SR VA and VA dagger. And then we have also a counting process, and so we have N R and how should I call it? Maybe N S N plus 1 goes to N S. I'm sorry, N S N plus 1, which is equal to N N S plus delta RS, and it's with the same with the same probability. So this is just the counting. We count the number of times we have found counts. So this really is just counting the number of times that you have found an eigenvalue belonging to this subset S index little s has been found in the measurements. And I insist, I mean, I think you never insist enough on that this is really what is observed, measured, observed, and this is used to infer in particular, there is one variant of these equations. You can also play a different game, which you have to play in real experiments, in fact, which is this equation. But now you have an evolution for a rho trial. You have rho n trial, which is equal to rho n plus 1 trial, which is equal to rho n, I'm sorry, you see, the point is that it may very well be that you have very little idea of what the state of your system is at time 0. So if you believe that individual systems do have a state somehow, or if you, whatever, then you have a real evolution. But in fact, if you want to reconstruct the density matrix, you will have to make some approximation. Start from a row 0 trial. And then try to recover the true row by saying that, okay, if I make many measurements, perhaps I have a possibility to recover the true row. So and the question is, under which conditions row trial comes close to row at large times. And you see, of course, to do a row trial, the probabilities, nevertheless, they are really computed with that. I mean, the things happen really with this probability. So anyway, and what we saw the other day, so for non-demolition measurements, they coalesce exponentially fast. And this is an easy consequence of the computations I showed you last time. But there are many other instances for which, in fact, it's true that even if you start with a bad initial row, then after a while, nevertheless, the row you have is very close to the real one. And we shall see examples of that. So let me finish this first part of the lecture with...
Sorry? This is basically because the Markovian evolution doesn't remember the initial condition. Is it correct? Or?
I don't know how to make such a simple argument, in fact. Of course, I mean, of course, there is no doubt that the Markovian structure plays a role, but going just like that from the Markovian property to this statement is something I do not know how to do. And I think it requires more, because there are instances in which it's not true that the two come close together. You can cook up examples which are Markovian as the other ones, and for which there is no convergence. So I think it requires a bit more.
So do you know what is the missing ingredient?
No, I don't.
It depends on the...
It depends on the explicit operators you have. Yeah. And the fact that I don't know doesn't mean nobody knows. So I can try to have a look at the literature and try to answer next time. I'm not sure I will find an answer because this is not so well known, but maybe somebody knows, but I don't. All I know is that there are examples in which it doesn't work. Yes?
Sorry, I do not understand really what is the row trial. I mean,
it's just, well, for instance, you could say, okay, I don't know the system is in a certain state, but I don't know anything about it. So let us just start with row trial, the most disordered possible one, which is just proportional to the identity matrix. It's just I don't.
Ansatz.
It's an ansatz. Yes, you see and in fact, so let me say it again. So maybe this way of phrasing things is influenced by Bayesian statistics. In Bayesian statistics, what do? You have some phenomenon and you don't know anything about it, and then you learn something about it, and indirectly you change your estimate of the relative probabilities. There are many situations for using conditional probabilities. So in fact, if you look at the notes, I forgot to say it the other day, but in fact, there is one of the equations for non-demolition measurements is really an equation for standard Bayesian evolution. So have a look at the notes, and you will see what I mean by that. So it's just somehow you see the idea is that when you don't know a system and you learn things little by little, you can update your knowledge, and this is you can say that this is essentially an extension of the usual Bayes rule, and I don't want to talk about it now, but have a look at it. This is explained in the notes for repeated measurements.
Sorry, I'm sorry to linger on this, but if I don't think about it as a set of and as measurements, I'm just thinking about an evolution that is determined by these operators.
Yes.
These are Krauss operators or not?
Yes.
Okay.
These are yes.
So this evolution, which is unique. I mean, when this holds that the trials, the initial state doesn't matter, it means that you've selected a set of these operators that will take any density matrix to a fixed state. Is that correct?
Yes, but then in that case, it's somehow for small systems. This is not so deep or interesting. It just says that you have only one. The average evolution is the average evolution is just like in the Markov case. You have a single stationary state. Yes.
But it's the evolution of any initial state. It's not the average one, or I'm missing.
No. It's any initial state, but you use the average evolution. You don't do these things. You just take the average. So okay. Maybe I can conclude on that for this morning. So there is one case in which the discussion is quite easy. Is when you imagine special case is just to say that no reading of the measurements of the result of the measurement. And this is equivalent to averaging. And so this says that rho n plus 1 is just equal to sum over A belonging to S of VA rho n VA dagger, which is psi of rho n. This is, okay, so this, I call it psi. It's a capital psi. This is the super evolution, super operator. Okay, so then for this, you see this is just a linear equation, deterministic equation, and then the question is whether or not the solutions of this linear equation have a limit when n is large. And if you are in a non-degenerate situation for which this super operator has one as an eigenvalue, it always does, but with multiplicity 1, then you're guaranteed that whatever you start with, in the end, you get the same. At large times, they converge exponentially fast. Yes, because this is then somehow rho n is just equal to psi n of rho 0. And so psi is just a matrix, and you have to look at its eigenvalues. And if it always has eigenvalue 1, this is easy to see, and all the eigenvalues are smaller or equal to 1, which is a fact I don't know how to prove. In fact, but I'm sure some people know how to prove it. That for that case, some people know how to prove it. But this is a generalization of the standard theorem for Markov chains. I mean, whatever. But anyway, if one is non-degenerate and all the other eigenvalues have modulus strictly less than 1, then starting from any row, in the end, you just then, if psi has only one eigenvector with eigenvalue modulus 1, then this eigenvector, let's call it rho stationary, then rho stat, then, well, of course, rho n converges to rho stat, whatever rho 0, whatever rho 0. So this is somehow easy. I mean, of course, if the system is large, it might be difficult to diagonalize psi, but for small systems which we want to look at, essentially, this is, this is not a difficulty. And the question is, but you see, the point is that in fact, especially for non-demolition measurements, the point is that you have you have several fixed points, and nevertheless, this is degenerate, and nevertheless you have this for non-demolition measurement. This dynamics has fixed points, several fixed points, and it doesn't prevent the fact that in the end you go to a fixed point, and the fixed point is independent of the initial condition.
It's only dependent by the operator. It's only determined by the operator.
Well, and the randomness, because it's a random evolution, and the end state depends on the experiment you make. You see, this is random. So if you do the experiment one time, you will find that you converge to a certain state in the end. If you do it another time, it will converge to another state. But what is sure is that this depends on the initial condition. This state does depend on the initial condition. However, if you use a bad initial condition, but the right results of the experiments, the bad initial condition finally converges to the right state. Is that reasonably clear?
With the probabilities between the fixed points.
Yes. Okay, so maybe I will stop here and resume after a break. Okay, so now we can move to the second part, which is made of examples. So it will be a bit less abstract than the initial part of the lecture. And so what we want to do for a while is just find solutions relation, which is just sum over A VA dag VA is equal to the identity. Because this is the only constraint we have. So if we can enumerate solutions to these equations, then we can use them to do some at least numerical simulations or whatever, or have some ideas of how we want to model certain phenomena. Okay, so there are many things you can say about this. The first one maybe is you can call it randomization. Which is the same convex combinations. So you imagine that you have several solutions. So you have VA A belonging to S, V prime A prime belonging to S prime, blah blah blah. These are solutions. To star. All of them are solutions to star. Well, then it's easy to see that you can make convex linear combinations. So if P plus P prime plus P double prime plus blah 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 is equal to 1, then of course you also have the formula that sum over A P VA dagger VI plus P prime VA dagger prime VA prime prime plus P double prime VA double prime dagger VA double prime plus blah 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 is also equal to the identity. Okay, this is here. I'm sorry, I should write down a sum over A prime, a sum over A double prime. This one is going to be an S prime, S double prime. Okay, and then of course you can decide to incorporate the P, square root of P in each of these guys. So you put square root of P VI, square root of P prime V prime A prime, square root of P double prime V double prime A double prime, etc. And then you have new families of operators, and there are more than before. And for these ones, you will have all these you see all these operators. You will get an equation which is exactly star for a larger family of operators. So this is something you can always do. So this is the first obvious thing. The next one is taking the cardinal of S to be 1. I already mentioned it before. And then star is just saying that V dagger V is equal to the identity, and if the dimension of H is strictly less than infinity, this means that V is unitary. So, as a special case of our complicated random blah 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 evolutions, we have the case when there is only one possible result to the experiment, which means we make no experiment essentially, and V is unitary. And then by randomization, if sum over A PA is equal to 1 and VA is unitary, I'm sorry, UA is unitary for each A, then VA equal to square root of PA times UA gives the solution. To star, and you can call this random unitary evolution. I'm sorry? No. What is random is no. The P are given, but indeed, if you look at the formula, so let me do it in detail. Random unitary evolution. Look. What if you take these for the V's and you apply the formula that I probably just erased a second ago? No, I didn't. So let's imagine that we really read the result of the measurement. The result is going to be that rho n plus 1 is going to be UA rho UA dag with probability. This is I let you do the little computation that in fact if you do the computation of the trace, you will find that it's exactly equal to pi. If you do things above you see everything cancels, and this is rho n. So this is why I call this random unitary evolution. At each step you choose independently which unitary evolution you're going to have, and then you apply it. And you iterate. And of course, if you iterate unitary evolutions at random, you still get a unitary transformation, and you can study it. And then you can also look at the average. And on the other hand, if you look at the average, then this is perfect reading. Of course, this is still unitary, but then if you do no reading, then rho n plus 1 is just going to be sum over A, PA, UA, rho n, UA dag. And this one is clearly not unitary anymore, and you have to study in precisely the eigenvalues of this transformation, and in general, it's far from unitary. I mean, it's dissipative. This is dissipative. In general. And this is no reading. Okay, so this is another example. And now I would like to talk about two examples related to Markov chains. So I will start with a Hilbert space. So I imagine that H is our Hilbert space. Alpha is an orthonormal basis. Let's say alpha belongs to R, just to fix the notations. And then I imagine that now M alpha beta is a stochastic matrix. Which means M alpha beta larger than or equal to 0, whatever alpha beta, and with my normalizations, sum over alpha M alpha beta is equal to 1, whatever beta. So this, another way to state it is that this is the generator of a Markov chain. Is this familiar to everybody, essentially? Well, I guess this is quite well. Markov chains are quite well known everywhere. So I guess. So I take this, and associated to this, I will exhibit at least two solutions of the closure relation. And I claim the following, and I will let you check it, but before I claim it, I have to have a look at the precise formulae, because, of course, the devil is in the details for that. So the first one is to take beta VA alpha is equal to square root of M beta alpha delta A alpha. Let me just check. Yes, that's correct. So, and I take A belonging to R. And the other one is give the solution. So this is a computation. It's an easy computation using all the rules. And in fact, there is another one, beta Vx alpha, which is a bit more complicated, but I guess the formula is going to be, maybe it's easier if I have the notes instead of looking at the I should be close. Okay, so these are claims. So it's easy to check. I mean, I give you the two formulae explicitly, and then you plug in, you compute this, blah blah blah, and you go on. And well, this is just elementary. And what is interesting for both of them, the average evolution on the diagonal is the standard Markov chain master equation. Which means that rho n plus 1 alpha alpha is simply equal to sum over beta m. So let's try to do it in the right way. M alpha beta rho n beta beta. So that's something you have to check as well. But in fact, what I want to stress, and you can have a look in the notes to have the details, is that in fact, so on the diagonal, you really recover. You see, this is just the evolution. The evolution would just be, you would write it as pi. This is just the distribution of probabilities in your chain. Pi n plus 1 alpha would be equal to sum over beta m alpha beta pi n beta. This would be the standard equation for the Markov chain. But in fact, these two solutions, they have very, very different physical properties, and the difference in physical properties can be traced to the following facts. That you see, this is a good exercise because, as you know, if you have a Markov matrix, M alpha beta is just describing how you can move from state beta to state alpha with the way I wrote it. M alpha beta is proba to go from beta to alpha. And so this here is just saying that the probability to go somewhere is equal to 1. This is the standard notation. So they describe the possibility to have a transition from beta to alpha. So now if you look at this formula here, they say that in fact the operator, you see the operator VA is breaking M in little pieces somehow, and you see that in that case you are allowed, you have a constraint on the initial state. VA takes the initial state alpha but takes it anywhere with a certain probability, whereas in this case Vx you have to start from there must be a mistake. This is not beautiful. I guess this is the right result. I will have to check for the next time. So this Vx is going to describe transitions which are much more restrictive because Vx will only allow transition. X is equal to AB, and it will only allow transitions from A to B. So it's really, this one has broken somehow the matrix in columns, and this one has broken it down up to its matrix elements. It governs. So this means that you are in contact with an environment, and for this first kind of environment, there is a single you see, you are putting your system in contact with several reservoirs or whatever, and in this case, there is one reservoir that is able to send state A anywhere, whereas for the other ones, the reservoirs that are around, they are only able to trigger much more restricted transitions. So there is some kind of semi-classical, if you want, interpretation of the operator of the operators V. And this can well, this is useful. I mean, I will not give the example of the double dot today, but this is one of the things you can try to rely on if you want to induce certain transition. You say, okay, I want something that triggers the entrance of one electron in the system, or that triggers that one electrons leave the systems and all that. You will enumerate all the elementary processes, semi-classical processes you can have in mind for your system, and for each of these semi-classical process, you will introduce a certain operator VA, and if you did your job properly, you have a reasonable modelization of the system in the end. Okay, so there is one last thing to note, is that, again, I let you have a look at the notes, but if I'm not mistaken, in fact, so the second one is extremely decoherent. Which means that after one time step, all the coherences in the density matrix have disappeared, and the other one is extremely purifying, in fact. So this is yet another warning that indeed, so you see, you have the diagonal of the density matrix is totally, the evolution is totally, the average evolution for the diagonal is totally insensitive to which model you take for your VAs. However, one of them purifies in one time step, the other one decoheres in one time step. So you really, there is some, you see, there is really some physics to put in the operators V, and the physics that cannot be avoided. I mean, it's, you really have to think about your system and try to model it in a physically relevant way. Somehow there are few mathematical constraints in this game, and then you have to think about physics to do something reasonable. Okay, so now we come to a part which is, so these are families of general solutions. There are many others. Oh yeah, okay, so there is one last, which is maybe worth doing quickly, which is very easy. It's just the case, we just want to look at the case when the cardinal of S is equal to 2. So you see you have V dag V plus V prime dag V prime is equal to the identity. And then the right trick is to use the polar decomposition. So you will say that V is equal to U times L to the 1/2. This is a positive matrix. This is unitary. And then you will immediately realize that, in fact, you can write down that V prime is equal to U prime times 1 minus L to the 1/2, and L is a positive matrix or operator with spectrum in the interval 0, 1. So that L makes sense, and N to the 1/2 makes sense, and 1 minus L to the 1/2 makes sense. So this is the general solution when S is equal to 2. So this is something you can use, and then you can even specialize more by looking also at small dimensional, well, make a finer description when h is equal to 2, which is essentially enough for most of our needs. Because if h is equal to, the dimension of h is equal to 2, you can also describe explicitly unitary matrices by explicit formulae and all that, so this is really easy. Okay, so now we can turn to something which is maybe more fun, which is how would we which is Rabi oscillations observed by indirect measurements. So what is it? So what we do is we take simply h to be equal to C2 and just Rabi, so and we take a basis alpha, orthonormal basis, and we assume that the system evolves by a unitary but is observed by non-demolition measurements by a unitary. Let's make it more precise, for whom the alphas are not eigenstates, but is observed via non-demolition measurements with pointer states alpha. So what does that mean? So imagine first you turn off the unitary evolution. This means that you are really in the situation we had last week. We just let the probes go by, and little by little you discover, you measure, and you discover that you find your system in one of the states alpha. Alpha is equal to 1 or 2. But now you have also the unitary evolution that is going to rotate the states alpha. So in between the passage of two probes, there has been a small rotation. You make your measurement, then another small rotation, then your measurement, and so on. And if you, the way to model this, which is a bit naive, of course, we're going to make a very idealized description of such an experiment, because we are going to imagine that when the probes go by, we stop the Hamiltonian evolution. So we let evolve using the Hamiltonian, then let the probes go by and make the measurement, and then turn on again the Hamiltonian, and blah blah blah. But this is just an illustration. I mean, it could be refined to have something more precise. But anyway. So we imagine that u is just equal to something very simple like cos theta sine theta minus sine theta cos theta. So I want to be in the I want to use a basis for whom the u is given by just stupid rotation, a simple rotation, and then we have two measurement operators, which are let's say v and v prime. And I will take something like v is equal to square root of p square root of q 0, 0. V has to be diagonal because we are doing a non-demolition measurement in the basis alpha, and v prime is just simply equal to square root of 1 minus p square root of 1 minus q 0, 0. And the fact that they are diagonal we could also include phases and things like that. I mean, just to simplify, I just take the two, then PQ belong to the interval 0, 1. And we could have more complicated solutions to these equations even on the diagonal. But well, indeed, we could multiply by arbitrary phases here, there. Well, just at will. This is a bit trivial and doesn't change much what is going on. But okay, and they are diagonal, which is equivalent to non-demolition measurements. In the alpha basis. And so if you, okay, yeah, prime. Okay, so this is a nice exercise. So you can, so now you have enough. So if you want, you can put the two of them together and you can, maybe I don't know, yes. So I imagine, so what happens to the density matrix is that rho goes to U rho U dag. This is during the unitary evolution, and then there is the internal unitary evolution, and then there is the interaction with the probe and the measurement, and then you get V. This is what I call rho prime, and this is rho double prime. So this is going to be V rho prime V dag divided by trace of V rho prime V dag proba trace of V rho prime V dag. And this is what I call rho double prime. And the map rho n goes to rho n plus 1 is rho goes to rho double prime. So you make a small amount of unitary evolution, then you measure, then you make another small amount of unitary evolution, then you measure again, and so on. Okay, so now I think you've suffered enough, and we can have a look at some of the little things. On the blackboard, okay. C'est vrai, I'm sorry. Okay, sorry. So here is, I have to turn on, yes, just a second. Yes, it works. Little by little, it starts to appear. So here is the here is what happens if you only have the unitary evolution. So I have chosen a small time step, well, an arbitrary time step, because I don't even know if there is a number here. So the time step is not important. But I have chosen the theta to be small. Theta is a small number. So we see, because if theta is large, so you can really see it's almost like a continuous time evolution. And these are Rabi oscillations. And this blue line here is just, okay, so if I decompose, I use, so assume, take real rho 0 and write it as 1/2 times identity plus x, let me put it in blue, sigma z, plus, I'm sorry, this is really a bad notation, but nevertheless it's quite standard somehow. K, this is bad, but So, and this defines the eigenstates of sigma z are the pointer states. To say it differently, essentially the blue curve is for the diagonal element of the density matrix, and the red curve is for the off-diagonal element of the density matrix. You see, K is for sigma x and x is for sigma z. Okay. So this is what happens if you only put Rabi oscillations. And now imagine that you start to make measurements, but for instance, okay, so maybe we could even say things a little bit differently. Let us make here, choose a certain number K. And you see, you do a certain number of unitary evolutions, and then you measure. Okay, and then essentially here, this is not very okay. Anyway, so you imagine somehow that K is infinite, but theta is very small. So this is the picture you have, and now you will start to take a smaller K, so you make a certain number of steps of the unitary evolution, you measure and all that, and so the smaller K, of course, the larger the influence of measurements is going to be. So let's see what happens in the next transparency. You see, due to the measurement, the evolution of the density matrix, this is just a sample, I mean there is randomness in it, and you see that you start to deform a little bit the Rabi oscillations, but you can clearly still see that there are oscillations. And what is funny on this little picture is, you see, I decided to choose a density matrix which wasn't pure, and which means that at no time is there a chance for x, for instance, to go to the value 1. I mean, at no it's not a pure density matrix. But if you look at what happens as soon as you turn on measurements, you see that at some points the off-diagonal coefficients become 1, or the diagonal coefficients become 1, and in fact, we shall see in a moment, if we have time, that the introducing measurements means that there is exponentially fast purification in the system. So, which means that here you see the system isn't pure, and it gets more and more pure as time goes by. If you would plot something that characterizes for a density matrix the fact that it's pure, you would see that really you have purification which is exponentially fast. And then you go on and you measure more and more often, and you see, if you look at this picture, it's already essentially impossible to see that there are oscillations, regular oscillations. I mean, the blue, it's really becomes really irregular, and you make the measurement stronger and stronger, and this is what you see. And the extreme looks like this. That, in fact, due to the measurement, what was Rabi oscillations, if you observe them, in fact, they turn into jumps. So you spend most of your time in one of the pointer states, then abruptly you jump to the other pointer state, you spend a lot of time in it, jump abruptly back to the first one, and go on. It's not even obvious, but probably, I guess probably here we go back to zero and stay for a while here. So this is typical. So this really is the important thing to remember is that this leads to predict the observation of quantum jumps. Yes.
How often is the measurement performed on this time scale?
Well, in fact, many. Okay, so so that's a very good question. In fact, you imagine you can. If you when we studied non-demolition measurements, we saw that there was a typical time scale on which you would decide, the system would decide if it's in which state it is. You see that, but this requires many measurements. So you see that in the time scale we have chosen now, it takes just essentially. You see, this is really a vertical. This is something that was. Do I have any chance to show you a picture? Okay, so this means that in fact we make the indirect measurements so often that in fact it becomes essentially a classical a standard apparatus for which the collapse is immediate. You see, because you go just in a very short time from here to there. So on this time scale, you collapse instantaneously, essentially.
And this is also what it looks like somehow uncorrelated noise, right? Or maybe correlated. I can't say.
This one here.
No, all the noise on top of the plus.
Yes.
One.
Okay, so this is something we shall. I shall tell you how to describe precisely in the next lecture. But indeed, this is uncorrelated noise. Yes, that's correct.
Because you're measuring too fast, and every time it's because it's measured very.
Yes, yes, that's correct. The noise becomes uncorrelated in the limit when you measure very fast. Yes, that's correct. Yes. If not, it's correlated. If you would zoom, it's possible to zoom on these things because there are probably there are millions of measurements in between these two events, and you can zoom. And when you zoom, you see structure, and this is not uncorrelated. This is clearly correlated. Yes. It's uncorrelated at this on this time scale. Yes, definitely.
And if the frequency of the measurements goes to infinity, you get stuck forever in one state.
Okay, so that's a good question that I didn't want to talk about that. No, you don't get stuck in one state forever. However, in this example of Rabi oscillations, if you keep theta fixed somehow and you measure more and more often, the time it will take to see a jump will explode. Okay, so these pictures have been made by scaling at the same time. I will show you how to do that next time. These pictures have been made by scaling theta and okay. Maybe I can go back to the blackboard and make some now that we have seen the pictures. But you see, well, maybe not that one, but I guess this experiment is made in labs, and you see, this is really one of the I don't know how I should say the Gedanken experiments of the founders of quantum mechanics. Somehow, I mean, you really see quantum jumps, and they are the fathers of quantum mechanics did not really associate jumps to measurements, but nevertheless, this is this is striking. You really see quantum jumps at work. So, why should I say? So, there is an interesting. Let's say there is an interesting regime. For whom a single measurement or a single U step has a small effect on rho, so which means theta is small, and a single measurement should have a small effect. This means that in the notations before, so this means theta small and P minus Q small, in fact. If you want the effect, you see, if you want the effect on the density matrix to be small, you see P and Q are the things that decide whether you are in the pointer state 1 or 2. And so if they are equal, essentially, so this means the corresponding V's are proportional to the identity. They don't make the difference between the two pointer states. If P is close to Q, then the matrices V are close to the identity, and so it's easy to see that all these things become small transformations, and these are small transformations because due to the smallest of this difference, the measurements on the probe do not really have a hard time to distinguish between the 2 pointer states. Okay, so and it is okay. So this is small, and then we can look at the time continuous time limit. And this is our job for the next time, in fact. Is to take the continuous limit of our general equations and try to understand what they mean. But what I can say very well, this is essentially obvious, is that theta should scale something like omega epsilon. This is the time step. And what is maybe less obvious, but maybe not so surprising, is that P minus Q should scale like epsilon to the 1/2. Okay? And then if we let n go to infinity, nt, and epsilon equals t finite, well, our evolution equations turn into well, have a continuous time limit. Okay, and now to come back to what Grégoire said, we want to study the regime when only a small number, well, let's say when convergence collapses fast, let's say. Okay, and this so because okay, so you can look at different values of omega, gamma, and all that, and we want to study a regime when collapse is fast, and this means that we won't let gamma go to infinity. And then, indeed, in that system, there is something called the quantum Zeno effect, which is an important physical thing that is also observed in experiments nowadays. When gamma is large. The time between two jumps diverges when gamma goes to infinity. Okay, and what is interesting is that the thing is now, however, if omega scales like gamma, then there is a finite limit.
But you're taking epsilon to 0 also.
Yes, epsilon is very small. Well, yes.
So can you scale all of them?
You take epsilon very small. Let's say 10 to the minus 10, I don't know. And then you look at what happens when you change gamma and omega. And of course, if you take omega so large that omega epsilon is larger than 1, you see, the point is that we want these, you take epsilon small, and we want these to remain small, in fact. But if epsilon is very small, it doesn't prevent you from taking a reasonable gamma. Let's say, for instance, an example, and maybe it's even realistic for the picture I show. The example, you take epsilon is 10 to the minus 6, let's say, something like that, and you take gamma is equal to 10, and omega, which should scale like gamma, is also equal to 10. So they don't have to be equal, they just have to be of the same order of magnitude, so take equal to 20. So you see, if you do that, this is still of order 10 to the minus 2, so this is small. It takes many measurements to really have collapse, but okay, not so many. This is really small. This is 10 to the minus 5, 10 to the minus 4, so this is really small. And taking the two together and making the picture, you will see a picture like this one. However, if you take omega much smaller than that, so if you say I want to keep omega finite, so let's say take omega equals 1, then you will see something for whom this will last forever. You will remain forever essentially in the same. Well, if typically you have 5 jumps in this, well, you will have 20 times less jumps, so there will be no jump on the picture essentially.
This is exactly the quantum Zeno effect, right? Or is it something?
Well, the quantum Zeno effect, you can study it, but yes, this is exactly the quantum Zeno effect. The quantum Zeno effect, you can do it with brutal measurements. So you can do it with instantaneous measurements, the quantum Zeno effect. This is an analog for indirect measurements, but this is the same physical effect. It's indeed, if you do, it's quite easy to see if you do some scaling that basically, if you measure, well, basically, if you're in an typical, well, where does the quantum Zeno effect come from? It tells you that the overlap between you have your unitary evolution and n prime, and this is going to be delta n prime plus something. If this is 4 times epsilon, this is of order epsilon squared. You see? This is an easy computation if you have to, well, this is easy to do. And so the point is that if you measure after time epsilon, you typically don't have had the time to change eigenstate between, because this is too small, and you will stay forever in the same state. So this is something you can do with abrupt measurements. This is, and the scale, well, yes, it's really the standard quantum Zeno effect. The scalings are compatible and then whatever. Yes.
Is it just because you repeated this weak measurement enough times in order to have the same effect as one projective measurement?
Well, this is, you see, if you look at the picture, indeed, somehow you have the feeling that this is just one measurement. I mean, yes, you are in this limit. What is something that you never see if you do brutal measurements and not indirect measurements is all this uncorrelated noise. This is really typical of indirect measurements.
If you set p minus q equal 1, you're back to the brutal case.
Yes, indeed, yes.
And the noise disappears.
If you do that, yes, it's probably. It's true because indeed because the system is 2 by 2 and the probes are 2 by 2 as well, you can indeed with just one measurement collapse completely. You're perfectly correct. Yes. If we would do the analog for a larger system, we wouldn't be able to collapse just by observing a 2-level probe. We couldn't be able to make it collapse in one step, but here you can do it exactly. I agree with it. Yes.
And last question. In this system, it's also a weak measurement. When you say indirect measurement, how does it relate to weak measurement?
Well, you first have to tell me what you call a weak measurement.
That you don't disturb the system a lot.
Well, it is indeed a weak measurement because these things are small. Yes.
That you don't learn basically that the condition that you said, the overlap of the state after the measurement is almost.
So it's also a weak measurement. Yes, definitely. But and in fact, so there is a whole theory of measurement in quantum mechanics, and but somehow it turns out that even if there are many ways to realize these measurement techniques, in the end, they can always be realized by indirect measurements. I don't know of any counterexample, but maybe there are some. But all the things you do in the lab, very often they don't look like indirect measurements, but nevertheless the mathematics that the equations you get in the end are the same as the ones you would get from indirect measurements. I think we should stop for it, isn't it, Ricardo?
You may go on for 10 minutes if you want.
No, it's late, no, isn't it? Okay, so I don't want to start another one, but let me show you just in 1 second the purification story, because I think it's nice mathematics and it's not too difficult. So let's look at it. So purification in that case. So we are going to purify. Which is something you don't have to, this is true, I mean, so purification. So this is a nice little trick. It's the following. So you see, I've told you many, many times that there are compensations between numerator and denominators in this case. And we are going to put this to good use by doing the following trick. So you see, when you take the average of rho, essentially, this compensates this, and you get a sum, blah, blah, blah. Now, there is another thing you can do. Imagine that you look at the determinant of rho, and rho is 2 by 2. Okay? So, of course, this doesn't look too good, because the determinant of rho, you see, it's a random object. It's going to experience this transformation. And you will have the square in the denominator, but you will, when you make the average, you have only a power of 1. So this is not a good idea. But now look at the determinant of this to the 1/2. Okay? And imagine that now you average, and it's easy to see. You do the expectation, so you compute the average of determinant of rho n plus 1 to the 1/2, let's say, knowing things up to time n. I don't want to explain conditional expectations, but it's knowing things up to time n. So I simply imagine that I know rho n, essentially knowing rho n if you want. Because this is Markovian, so essentially knowing rho n is enough to know everything up to time. Well, is the same as knowing everything up to time n. For what concerns the future. Okay, and then it's very easy to see that this is just, you see what happens. Because of the factor 1/2 in the average, this will compensate with this. Because in the determinant, this will appear squared, but we take the power 1/2, we average, this disappears. And here, we just have to take the sum. Well, this will not count at all in the determinant, because the determinant of a unitary transformation is 1. And these ones, let me remind you that V was equal to square root of P square root of Q 0, 0. And V prime was equal to square root of 1 minus P square root of 1 minus Q 0, 0. So if you do that, you will see very easily that this is exactly square root of PQ plus square root of 1 minus P 1 minus Q times the determinant of rho n to the 1/2. You see? This is just a little computation. I mean, easy computing, you see. The determinant of V is equal to this. So V, okay. You have V dag, they have the same determinant, but then you take the power 1/2, so you don't take you see just the power 1. Okay. This is just an obvious computation. Now, I claim that this, if P is different from Q, which means that you make a difference between the two pointer states, then this is always strictly less than 1. Why is it so? Well, this is the Cauchy-Schwarz inequality. Look, if I write down sum over A xa ya, we know that this is always less than sum of xa squared, sum ya squared to the 1/2. So here what do we have? So this is x1, y1, this is x2, y2, and so this is smaller than p plus q. So this is less than p plus 1 minus p, I'm sorry, q plus 1 minus q. And equality only if p equals q. Okay, so this means that in average, this quantity is decreasing. And is decreasing significantly because this is strictly less than 1. So it takes a mathematical theorem, but so at least it's easy to see that the expectation of this determinant goes to 0 very fast, exponentially. And this is essentially enough to convince you that even because the expectation goes to 0 and this is positive, the random variable itself has to go to 0. This is a bit too fast for such a to assess such a convergence, but there is a martingale convergence theorem, blah, 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 which tells you that the determinant is going to 0. And if this is true when you put the power 1/2, this is also true when you don't put the power 1/2. And the fact that the determinant of rho n goes to 0 for 2x2 matrices, this is equivalent 2x2 matrices. This is equivalent to purification. Because for 2x2 density matrices, pure states are exactly the ones with the determinant 0. So you see, and it works incredibly well. I mean, if you look at it, so here you see no measurement and no, no purification. And here you see at that point you are in a pure state, at that point you are in a pure state. I'm sorry, at that point you are in a pure state, at that point you are in a pure state. And then in fact all in between, but you would have to compute the determinant of the matrix, so you would have to compute the sum of the squares of these two guys. It's always equal to 1. In fact, if you look at it gently, the sum of the squares is always equal to 1. When the blue is 1, the red is 0, and then the intermediate states are satisfied as well. Okay, so maybe that ends what I wanted to say about Rabi oscillations observed by indirect measurements. So I stop for today.